Okay, hello everyone. We are very excited to welcome Lihua Lei today from Stanford University, who will be talking to us about double robust two-way fixed effects regression for panel data. After Lihua's talk, we have Jeff Wooldridge from Michigan State University that will be leading the discussion. Questions today are handled by Dominic, is that right?
Yep. All right, yeah, so as usual, please submit your questions in Q&A. We have two collaborators in Q&A today. We have Guido and we have Dimitri, so please submit your questions, and some of them will also be selected and discussed directly with Lihua. Yeah, with that, that's all from us. Lihua, please take us away.
Thanks for the introduction. Let me share my screen. Does that work? Okay. All right. First, I would like to thank the organizers for inviting me. It's my great pleasure to share one of my recent work on how to use the assignment model to make the two-way fixed effect regression more robust. And this is a joint work with my amazing collaborators, Dimitri Arkangelski, Guido Inference, and Xiaoman Luo. And if you follow the literature on diff in diff and panel data analysis, you will see that there is a exploding literature recently on making the existing estimators more robust or proposing new estimators. But just to make sure we're on the same page, so this celebrated two-way fixed effect model is just a regression specification that assumes that the outcome can be decomposed into the unit fixed effect, the time fixed effect, and a treatment effect term, and a covariate term, and an error term. So here, the unit and time fixed effects can be viewed as time invariant and unit invariant unmeasured confounders. So motivated by this model or this regression specification, we can define the two-way fixed effect estimator as the OLLAS estimator for tau, for this coefficient. And in the special case where you only have two time periods, and the unit only gets treated in the second period, this is equivalent to the standard DID estimator. And in general, if you have this two-way fixed effect model that is correctly specified, then we know that this estimator is unbiased. However, in modern causal inference, we typically don't start with a model. We want to think about an estimator through a broader lens. So it turns out, not surprisingly, without any modification, the two-way fixed effect estimator is going to be biased if some of the key assumptions in the two-way model is violated. So for example, here you can see in this term, we implicitly assume that the treatment effect is a constant. But if there's heterogeneity, then this estimator is no longer unbiased in general. And also, the first two terms will give us the parallel trend assumption. So if this is not true, then we also have bias. And recently, because of this concern, people propose a lot of alternative methods that try to remove the bias. And here I just list some of them, but this list is way longer than this. Okay, so here for us, the key question is, given so many works around, do we fully understand the two-way fixed effect regression estimators? And I guess the answer is no, otherwise I wouldn't have written this paper. So here is a sketch of today's talk. So I will start by introducing a class of estimand called W average treatment effect, or data in short. And then I will propose a new estimator called reshape IPW two-way fixed effect estimator. So here the IPW part is almost the same as the IPW estimator for cross-sectional data, but we have this reshape component, which will be defined later. And turns out this estimator permits valid design-based inference in the sense that if we know the assignment model, then this estimator will be consistent for a certain date, even if the treatment effects vary with both time and units in an almost arbitrary way. And we establish this result in a finite population framework, and we don't want to restrict it to staggered adoption. So we want to handle the most general case where the units are allowed to opt into the treatment and out of treatment at any time, But of course, staggered adoption will be an interesting special case. And also, this design-based results holds for many dependent designs in the sense that we allow the assignment to be dependent across units. So this includes things like sampling without replacement, two-stage randomization, among others. And then in general, when we deal with observational study, we don't know the assignment model, so we have to estimate it. And in this case, we will show that this estimator is doubly robust in the sense that it will consistently estimate the estimand if either the treatment assignment model is known or well estimated, or the two-way fixed effect model is correct. So that's like the outline of this talk. And let me start with the first part on defining the estimand, the estimator, and also the design-based inference result. So throughout this talk, I will consider a case with a balance panel where we have n units and a capital T time period. And in this talk, I will focus on the case where the capital T is fixed. And one point I want to make is that this is actually harder than the large T case in our context, because if you have the unit fixed effect, you can imagine that for each unit fixed effect, you only have capital T samples. And if that's the case, then the unit fixed effect cannot be consistently estimated, even if you have a correct model. So the fixed T case actually makes things harder. And then I will focus on the case where we have a binary treatment, and I will use WIT to denote the treatment. And furthermore, because this is panel data, I'm going to use this boldface WI to denote the treatment path, which is the vector of the treatment assignment. And here I will use pi I to denote the distribution of this boldface WI, which can be regarded as a special case of the generalized propensity score, if you view this as a multi-value treatment problem. And then for each unit and I and each time t, I assume there's a pair of potential outcomes YIT1 and YIT0. So for staggered adoption, we know we can make it more general by defining it in terms of the cohort, like in terms of the time of adoption. But for general design, you can either generalize this to allow for 2 to the t treatment assignment, or you can stay in the static case. So here we would stay in the static case to illustrate what's going to be surprising in this case. And then we will assume SUTVA in the sense that YIT equals to Y1 if it's treated, and Y0, YIT0 otherwise. So for this part of the talk, I will assume that this pair of potential outcomes are fixed with essentially no restriction, other than some restrictions on the magnitude. So it cannot be too large or too small. So this is a finite population framework, and we will only consider the randomness from the assignment model, from the assignment process. And given this set of notation, I can define the unit time-specific effect as the difference of YIT1 and YIT0. And I will call this tau IT. So again, I want to emphasize that we don't want to restrict the heterogeneity pattern of this tau IT. So we'll allow this tau IT to vary with both time and unit. And then to define an aggregated effect, what we're going to do is we first take an unweighted average of tau IT across units. And this is the second, this is this term. And this is essentially a time-specific AT. And then we will aggregate this time-specific ATE by a user-specified weight, called that Causal T. And an important special case is the equally weighted date, where we simply use 1/NT for every unit and every time period. And the reason we call this W average treatment effect is that we consider average over both directions. So in this talk, I will illustrate a lot of things using this equally weighted date. But I want to say that in practice, this is also a reasonable estimate, because here the weights are super interpretable. And in general, we might want to consider more general estimate by allowing Causal T to vary with T. So for example, we might want to put more weights to the later stage. But in any case, as long as these weights are user specified, we know that this estimate is interpretable. So we don't want these weights to be driven by the data. So when we have the assignment model, the first thought is to use IPW estimator, because this is how we handle the assignment model in the cross-sectional case. And in particular, we can look at this Hayek IPW estimator, which is basically the same as the standard version of the IPW estimator, except that now we're normalizing each estimate of the treatment arm specific effect by the sum of inverse propensity score. So instead of using the sample size, we're using this. And under the standard asymptotic argument, we know that this will converge to ATE. And interestingly, there's another formulation of this estimator. So turns out we can reformulate this as a weighted least square estimator, where the first part is the least squares objective, which only involves the intercept and the treatment assignment. But then instead of using the Euler-Last estimator, we're going to reweight this least square objective by the inverse propensity score. And via some tedious algebra, you can show that this estimator is exactly identical to the Hayek IPW estimator. So although this is a simple formulation, but this does bring us a lot of insight, because we see that here, when we talk about weighting in causal inference, we usually mean weighting the samples. But this gives us another strategy to weight the objective function. And at least operationally, you can easily imagine that we can extend this approach by changing the regression specification in this objective part. So in principle, we can allow for any regression specification. So then when it comes to the panel data, we can imagine that we can change this least square objective to the two-way fixed effect objective by including the two-way fixed effect. And this will give us a version of IPW estimator defining this way. But now the question is, does this IPW estimator estimate anything sensible? Or put in a more technical term, what's the statistical limit of this IPW estimator? So to answer this question, I will start with two simple examples, both with 3 time periods. So in the first example, I imagine a case where the treatment assignment, or for each unit, they will get at most 1 period being treated. So this could happen in things like a marketing experiment where the treatment is a coupon. So within a time range, every user gets at most 1 coupon. Or you can also imagine the case of the natural disaster, in the sense that within a short time range, there could be at most 1 natural disaster. So in this case, we can show that under standard assumptions, the IPW estimator will converge to the equally weighted date. So this shouldn't be surprising because everything is symmetric. So it seems like this is very intuitive. But this maybe, so we're attempting to think that this can be generalized to other designs or to other possible assignment. But let me give you another example on staggered rollout. In this case, every unit, as long as they get into the treatment, they will never leave. So this is pretty common in the policy setting, where as long as each state get into the treatment, then at least within a time period, they will never leave it. So the policy will be there. And in this case, the support of the treatment path will change. And turns out, under the same set of assumptions, we can show that the IPW estimator will converge to some date, but here the weights are no longer equal across time. And the weights here are 0.3, 0.4, and 0.3. So the good thing is this is still a date. So, and it has non-negative weights, but it is not as ideal as the equally weighted date because here the weights do not seem to be interpretable. And more generally, we show that if you're using the IPW estimator, then it will converge to a certain date. and they always have a non-negative weight. Here, we need some regularity conditions, but basically it's about overlap and limited dependence, because here we allow the treatment assignment to be dependent across units, and also some bounding moment assumption that restricts that the potential outcomes cannot be too large or too small. But essentially, we don't restrict the heterogeneity pattern of tau IT or YIT. And we show that this weight is proportional to some eta t times 1 minus eta t. And here, eta t is simply the fraction of possible treatment assignment for which the t's period is getting treated. So back into this example, we show that if you look at the first time period, then only the last assignment path has WT equals to 1. So there's 1 out of 4 assignments getting WT equals 1. So in this case, eta t equals to 1/4. So cosine t will be proportional to 3/16. And the same holds for the last period, because the first and last periods are kind of symmetric in this case. But for the second period, 2 out of 4 assignments have WT equals to 1. So here, this cosine t will be proportional to 4/16. That's why we got 0.3, 0.4, 0.3 weights. And if we generalize this result to T capital period, to capital T time period, then in the transient case, we can show that IPW estimator will converge to the equally weighted date, as in the tau example. But for staggered rollout, this will converge to a date where most of the weights are in the middle. And for the first and last period, we will have a little weight. So again, this is not a crazy estimate because we have non-negative weights across all time periods, but it's hard to justify this weights in an interpretable way, because let's say if you have 30 time periods, that means you will put most of the weights in periods in time 15 and 16, and you will put almost no weight in time 1 and time 30. So I think it's very hard to find a case where this is relevant. So for us, a natural question is, what if the user wants a date with pre-specified weights, something like equally weighted date? So this is our main research question. And to address this question, we propose another estimator called the reshape IPW estimator. So here, this estimator is very similar to the IPW estimator, except that we will need one more component. And this component is a data-independent distribution, and we call it capital pi. And this distribution is defined on the support of the treatment path. So here, everything is the same, except that instead of using 1 over the propensity score as the weight, we're going to use another number divided by the propensity score as the weight. And that number is given by this data-independent distribution pi. So that means for different type of treatment path, we want to use a different number to reweight this objective. And first of all, we can see that this generalized the IPW estimator and the standard two-way estimator in different scenarios. So for IPW estimator, we can simply recover it using a uniform distribution, capital pi. And then if we have a randomized experiment where all pi I equals to some pi, then this will recover the standard two-way fixed effect estimator, because now the weight equals to 1. So in some sense, our IPW estimator is a generalization of both IPW and standard two-way fixed effect estimators. So now the question becomes like, how we are going to choose pi to make sure that our IPW estimator will converge to a date with user-specified weights. And here is the core of here's one of our core results. So it turns out if we are given the support and also a capital pi that has the same support, then we can show that the two-way fixed effect estimator will converge to a date with user-specified weights Kasai, if, and quote unquote, only if we have this equation. So this is a cryptic equation, and you don't need to understand math here. So the only thing is that this is a set of quadratic equations that only depends on the support, meaning that we don't need to know the data in order to get this answer, in order to solve this data equation. We only need to know what possible assignment could be in your data. So like in the previous case, if we know it is a transient treatment assignment, then we are only going to get those 4 assignments. And for staggered rollout, we also have 4 possible assignments, but it's a different subset. So that's the only thing we need to define this data equation. And this set of quadratic equations would have some constraint. So for example, because we restrict this capital pi to be a probability distribution, so we need a simplex constraint. And also we need everything to be non-negative. So this is a set of quadratic equations with some linear constraint. And in general, we don't know how to solve this because it could have infinite solutions or it could have 0 solutions. But fortunately, for many practical scenarios on this support, we can solve this in closed form. So this includes DID, transient, staggered rollouts, and crossover, among others. So that means if you have one of these cases, we can just use the closed form solution. But in general, if your case is beyond this, then we have a generic solver based on nonlinear programming. So I see there's a question in Q&A. Shall I take it now, or?
I think Dimitri is currently answering it, but you can also take it if you want.
Yeah, okay. I can answer this question. So the question is, the staggered situation is also static as defined here. In principle, the potential outcome can also depend on the previous time period. And yes, so here in this paper, we consider the static case where YAT only depends on the contemporaneous treatment assignment. But in general, you can imagine a case where you have dynamics. And for staggered adoption, this has been well studied because you can simply define the potential outcomes in terms of the time of adoption. But here, because we want to handle the most general case where the treatment can get into and out of the treatment at any possible time. So if you still want to allow the potential outcome to depend on the entire path, it's going to be challenging because in principle, you need to consider 2 to the t types of treatment assignment. So this has been studied, well studied in the biostatistics literature. But there, if you want to allow for this full flexibility, you can't allow this panel to be too low. Otherwise, you're going to have the curse of not dimensionality, but you just have too many things, and then you will run short of samples within each strata. And here we want to, so the one way to extend our work is to think of the short range dynamics and say, if you believe that the potential outcome can only depend on contemporaneous treatment assignment together with the past treatments up to a certain point, then there is a way to generalize our work, but I'm not going to do it in this talk. Okay, I see another question. I can take it. So is it possible to constrain the number of solutions to the optimization problem? Well, so here, this is actually not an optimization problem. This is just a set of equations. So in principle, we can solve this equation. And then in the case where it has solutions, it will give us all possible solutions. And I haven't talked about how to select one solution from it. But if you do have many solutions, you can definitely add a constraint on it. So for example, you may have some variance concerns, and you want to only look at those capital Pi's that give you a good variance. Then you can definitely add those constraints. But in any case, you can first solve all of it, and you can pick the one that works best for you. As long as the selection process doesn't depend on the data, then you won't run into selective inference issue. Then it's fine.
I also have one very short question, if you have time.
Yeah.
So let's say I want the reweighted date where like just put equal weights on each time period. Do you have some intuition in which case I would get like very large weights for pi, in which case I would get very small weights for pi? So like extreme weights?
Yeah, that's a great question. It ultimately depends on the overlap. So just just like in the cross-sectional case, where if you have extreme propensity score, then you would have a huge weight. So here we are having the same issue. So in that case, you can imagine using trimming, or you can truncating the propensity score at a certain point, or you can simply drop the units with extreme propensity score. Of course, that's going to change the estimate, but it's one of the fundamental issue. Or you can bet on your outcome model, so that if you put more faith on your outcome model, then you rely less on the propensity score.
Okay, thanks.
Thanks for the question. Okay, I'm gonna move on. So let me show you an example of the solution set, just to give you a sense of what that looks like. So here again, I will consider the same examples. And for transient treatment with free time period, we know that here the capital pi, because it's a probability distribution defined on this subset, so it's essentially like 4 numbers that sum up to 1. And we can show that the solution of the data equation is simply the convex combination of these 4 numbers, where the first one put all mass onto the never treated and 0 mass onto the others. And the second one put 0 mass on never treated and equal mass on ever treated. And then if you take any convex combination, this will be a solution for the data equation. So in particular, if you set lambda to be 1/4, then you will get a uniform pi. And this corroborates our finding that if you use IPW estimator, which correspond to the uniform pi, then we will recover the equally weighted date. So by the way, I forgot to mention that for these slides, I will only consider the equally weighted date as the estimate. So here, for transient treatment, the uniform distribution is one solution. But for staggered rollout, turns out the solution is a convex combination of these 2 mysterious vectors, where the first one is 2/9, 3/9, 0, and 4/9. And the other one is the reverse of this vector. And not surprisingly, the uniform distribution is not a solution, because we know that the standard IPW estimator will not converge to equally weighted date. But we can find a whole bunch of R IPW estimators that do give us the equally weighted date. So in our paper, we have the more general results with T time periods, but here it's just to give a flavor of the results. So before moving on to the next part, I first want to talk about the design-based inference result. So here, we can look at this R IPW estimators, and let's assume that the data equation has a solution, and we're using that one of the solution to define our IPW estimator. Then we can show that first, this is consistent, and second, we can propose an asymptotically conservative variance estimator and a valid what-type confidence interval for many practical designs. And this includes the Bernoulli designs where the WIs are independent across units, or sampling without replacement, or cluster-wise randomization, 2-stage randomization, and so on. So basically, as long as this is a dependent design that you can handle for cross-sectional data, then you can use the same machinery to generate a variance estimate for this case. And roughly speaking, this is because we can get a asymptotic linearity for this estimator. So that will reduce the panel case into a cross-sectional case, so that you can use all the existing machinery to get the variance estimate and confidence interval. So before moving on to the next part, I want to give you another interpretation of the data equation, which might be interesting. So here, again, this is the R IPW estimator. And recall that if we do have a completely randomized experiment where all pi I equals to pi, then this will recover the standard two-way fixed effect estimator. So essentially, the data equation will give us all completely randomized experiment for which the two-way fixed effect estimator actually works, in the sense that it will converge to a user-specified estimate. So if you're familiar with the recent literature on two-way fixed effect, you might think maybe this is a conflict with the literature that saying the two-way fixed effect has negative weights. But actually, it's not a conflict, because in the literature, we people often treat the assignment as fixed. So the negative weights are given by the case where you're conditioning on the treatment assignment. But here, we will treat the assignment as random. And a high-level point I want to make here is that when we talk about weights, we shouldn't jump into the conclusion saying some estimator has negative weights and the others don't. It's important to first specify the sources of randomness, because you may have negative weights if you assume this is fixed, but that negative weights will disappear if you assume the treatment assignments are random. So later on, if time permits, I can talk more about this. Okay, so that's pretty much about the first part. And I don't see any question in Q&A, so I assume I can move on to the next part. Okay. So in the second part, I will briefly mention the double robustness property of this estimator. So in order to talk about this, we first need to introduce the covariate. So here, let's say we have this time invariant or time variant covariates. So in the latter case, we just compress everything into one boldface xi. And here we will assume that this xi satisfies a latent ignorability assumption, which is a little bit technical. But for now, you can just assume strict exogeneity or the ignorability assumption, which is a special case of this. And then what we're going to do is we're going to use xi to first fit an assignment model. And for staggered rollout, we can view the time of adoption as an event. Then we can fit a duration model, say a Cox model. And for general designs, we can fit things like discrete Markov model and conditional logic model. So here, ignoring all the theoretical guarantees, now you can see, due to this panel structure, we have a lot more flexibility in modeling the assignment. So previously in the cross-sectional case, you basically just treat it as a classification problem or a binary outcome problem, and you can apply logistic regression or some machine learning techniques. But here, we have a lot richer structure so that we can apply many other models. And then we're going to use the covariate xi to fit an outcome model. And one tricky thing is, or one subtle thing here is that we only need to model the effect that will vary with both the unit and time. So just to clarify that, suppose we believe that the standard two-way model is correct, in which we have the two-way fixed effect and the linear term on the covariate, then we only need to estimate this interaction effect. We don't need to estimate the two-way fixed effect in order to do the regression adjustment. So this is crucial in our case, because as I mentioned in the beginning of the talk, we have a fixed t. So that means even if this model is correct, there's no way that we can estimate alpha i's consistently. But fortunately, we don't need that to be consistently estimated. We just need to consistently estimate this interaction term. So then once we define this, we can define our IPW estimator as the following. We first modify the outcome by subtracting this regression part from the outcome. And then we pretend our estimated propensity score is the truth. And then we compute our IPW estimators on the modified outcomes with this estimated propensity score. So everything else is the same once we modify the outcome and estimate the propensity score. So then we can show that this estimator is doubly robust in the sense that this will converge to the date if either the assignment model is well estimated or the two-way model is correct. So here the intuition is pretty clear. If the assignment model is approximately correct, then this will mimic what we have got in the design-based inference. And that will give us the consistency. But on the other hand, if the assignment model is wrong, but two-way model is correct, then basically this is a weighted least square estimator with the correct specification. And we know that once you have a linear model, as long as your weights are not too crazy, then it will give you a consistent estimate for that linear model. So that's why we can get this double robustness. And I saw questions in Q&A. So before taking the questions, I'm going to make one more comment on the connection with the literature. So in the literature, there are some other notions of double robustness. So for example, there's a paper by Santana and Zhao talking about doubly robust DRD estimator. And I want to emphasize that here, our notion of double robustness is very different from their notion of double robustness, and neither one has the other one. So in the case when the assignment model is well estimated, in our case, we don't need other assumptions. We don't need conditional parallel trend, because here we can allow all the units to be non-identically distributed, and we can also think about this in a finite population framework. So we don't need conditional parallel trend. But their outcome model is indeed more general than ours, because here we only consider the standard two-way model, which assumes a constant treatment effect and homogeneous trend for everybody. But as I mentioned before, our strategy is to reweight the objective function. So in principle, we can think about more general regression specifications. So one of our ongoing work is to make our outcome model more flexible. So for example, we can combine our techniques with Jeff's paper, which puts more interaction terms between the treatment assignment and covariate into the regression model. So similarly, we can also think about a case where we have the interaction between the covariate and the two-way fixed effect to allow for covariate dependent trends. And again, we can think about a RIPW version of that estimator. And in many cases, we can extend our outcome model to the more general ones. But again, I'm not going to talk about that in this talk. So here, let me take one question perhaps. So the question is, the distributions on a simplex frequently relate to the Dirichlet distribution. Could this make sense in our context? It turns out for many cases, we don't have the Dirichlet distribution. So here I would say the solution of the data equation is just, it's better to view that as a solution of a quadratic system. And we don't have a very good interpretation of that. And but in all cases, we have found it has nothing to do with the Dirichlet. Okay, so when we talk about double robustness, there are two types of double robustness in the literature. So the first one is what we call the weak one, which tells us that the estimator is consistent if either model is well specified, it is well estimated. But there's a stronger notion of double robustness, saying that on top of the weak double robustness, we will also achieve a smaller error if both models are well estimated. And turns out our IPW estimator is strongly double robust, in the sense that if these estimators are fixed, if the estimator for the propensity score and regression adjustments are fixed, then the bias of our estimators is in the form of the product of two errors, where roughly speaking, the first one measured the accuracy of treatment modeling, and the second one measures the accuracy of outcome modeling. And the actual definitions of these two terms are a little bit technical, so I'm not going to show that. But this just shares the same flavor as the cross-sectional case, where for AIPW estimators, you will have this product, meaning that if both models are estimated to a certain accuracy, then the bias of the estimators is going to be even smaller. And in particular, if the product is of smaller order of 1 over root n, then we can have valid inference under the same set of assumptions for design-based inference, as long as the propensity score and the regression adjustment are fixed. But in practice, of course, we don't always have this external data to give us a fixed estimate of those two things. And so this motivates us to consider crossfitting. So here, what we can do is we crossfit the propensity score and regression adjustment. And we can show as long as they are asymptotically deterministic, we will have the same conclusion. And moreover, we can get doubly robust inference in the sense that when we give a confidence interval, it's also going to be doubly robust. But here, in order to get inference result, we need the units to be independent. But again, we don't need identical distribution. And by the way, and this is not the standard crossfitting, because we just crossfit the nuisance parameters. And after we got the nuisance parameters, we're still using the whole data set to get an estimate for the RRPW estimator. So that makes our arguments very different from standard crossfitting. So in the last few minutes, I will show you a case study very quickly. So in this example, we want to study the effect of the state of emergency in early COVID-19 pandemic. So you may still have the memory of what's going on in 2020. And in the end of February, and the Washington is the first state that declared that state of emergency. And that's basically the start of everything turning to online. And that's basically the era of Zoom and other online meeting apps. So here, the state of emergency is a situation in which a government is empowered to perform actions or impose policies that would normally not be permitted to undertake. And in order to study the short-term effect on economic activities, we need some outcome measures. But here it's not easy to get such a high-frequency economic activity measures. But interestingly, where we saw this data from OpenTable that give us the year-over-year city diners for sample restaurants in 36 states in the United States. And this is like a snapshot. It's not from 2020, it's from a recent year, because you can see there's some increases in dining rate, which is not possible during the early pandemic. And you can imagine in the early pandemic, all the numbers are quite negative. And you will get something like this in a daily basis, which is great. And then our goal is to get the equally weighted date by using the state of emergency as treatment and using the dining rate during the first 14 days as the outcome. And we know that there has been a lot of paper on policy analysis in COVID, and we know it's very challenging. But this problem is slightly different. So first, the state of emergency was less confounded compared to many later implemented policies like mask mandate or lockdown, because this was almost the first policy that affects the vast majority of the public. So there wouldn't be some policy or temporal spillover from other policies. So that makes this problem slightly easier. And on the other hand, the restaurant industry is responding to the policy very swiftly. So therefore, it is immune to some long-term confounders. So that's another perspective that makes this problem more approachable. And another feature of this problem is that the declaration time, or the assignment model in this case, which is the time that the time to declare the state of emergency, is much easier to model than the dining rate. And that's because the dining rate is driven by many unmeasured behavioral variables, which is impossible to measure, especially in such a high frequency setting. But the declaration time is arguably mainly driven by two things. One is the progress of the pandemic, like how many confirmed cases in this state. And the second is the authority of the, is the attitude of the authority. So just to demonstrate our estimator, we will use three covariates. One is the state level accumulated confirmed cases. And the second is the vote share of Democrats to reflect the authorities' attitude. And the third one is the number of hospital beds per capita, which reflects the amount of medical resource. And here is the treatment status. And you can see for this sample of 36 states, there are never treated units. There's one always treated units, and there's quite an amount of variation in other states in the first 14 days. So here, what we are going to do is we treat the declaration time as an event, and then we use a Cox model to fit the distribution of the declaration time. But here, because we are looking at the propensity score, and the Cox model will only give us the survival function. So we can take the first order difference. We can take the difference between the consecutive ones to get the density which is the propensity score we need. So in particular, for any time in between, we can take the difference. And for the last period, we take 1 minus that to get the propensity score. And we know that as long as we apply the Cox model, there will be some assumptions behind it. And so it's always good to perform some goodness of fit test. And for the Cox model in particular, we know that a crucial assumption is the proportional hazard model. And this could be wrong in practice. So here, as a sanity check, we perform this Schoenfeld test, which is a goodness of fit test for the proportional hazard assumption. And at least we don't see evidence against this model specification. But a caveat is that we should never take the goodness of fit test as a certificate, because if it failed to reject, it may be just that this test is underpowered. But at least this is a good sanity check. And finally, we use the Cox model to fit the assignment, and we use the standard two-way model to for the regression adjustment. And our estimate is -4%, which is significant at 90% level. And as a benchmark, we also compute the standard two-way fixed effect estimate, which is -1.1%. And that is much smaller in magnitude than the RIPW estimate, and it's not significant. And here, as the last comment, you can see that intervals are wider when using RIPW estimators. But that's not surprising, because RIPW estimators is robust to many more things, including the heterogeneity, which is arguably the case in this example. And also, it's robust to certain violation of parallel trend, because we don't need conditional parallel trend if the propensity score model is correct. So
if you
here,
can, Hi, Lihua, if you can please wrap up within a minute or two so we have time for
yes,
this.
yeah, I will get to the last slide. Yeah, I will skip this discussion on negative weights and jump into the conclusion. So in this talk, I first talk about IPW estimator that converges to a date with potentially uninterpretable weights. So even if it has non-negative weights, but the weights are not quite interpretable. So that's why the IPW estimator is not that desirable. But we propose a remedy for this by introducing this reshape component that solves the problem in the sense that first, it permits a valid design-based inference for many practical designs. And second, it is doubly robust and work for general designs, which is not limited to staggered rollouts. And practically, they empower the users to leverage the information from the assignment model, because this is usually the piece of information that's ignored in practice. But in many cases, because the treatment is more structured than the outcome, so we could have a lot more information on that. And moreover, this estimator is easily computed from any existing software. As long as it supports weighted two-way fixed effect regression, then you can get this estimator. And finally, I'll say in general, the objective reweighting is a powerful general strategy. And you can imagine that you can combine this with Jeff's more general models, or you can even combine this with an event study to allow for other types of dynamics. So with that, I'd like to thank you all for your attention.
Thank you, Lihua, and thank you for finishing up quickly after the queue. There is a question in Q&A, but for the sake of time and for making sure Jeff has enough time to go through what he has prepared, let's move on to discussion, and then if we have time in the end, we can take the questions. Jeff, feel free to share your slides whenever you're ready. You are muted.
Yes, I just have to find the, as usual, Zoom tries to trick me by moving things around. Okay, hopefully those are the ones, except they're not at the top, and I'll put in full screen. Okay. Okay, so hopefully you can see my slides now. First, thanks to the organizers and Ying in particular for giving me the opportunity to comment on this really interesting and important paper. I have to say I've been toying with some doubly robust estimation based on some recent work I've done that Lihua mentioned in the staggered case, and I should also thank him for such a clear presentation. I learned a bunch just during that presentation, I think, and also for sharing his slides ahead of time, which made going through the presentation and then the paper a lot easier. So of course, as Lihua summarized, there has been a lot of scrutiny of the standard two-way fixed effects approach, where you assume a single treatment effect. And of course, one of the issues when we talk about biased estimation is we have to talk about what the target is that we're trying to estimate. So, but the recent work by these authors that I'm sure you're all familiar with showed that, in general, at least from their perspective, in the scheme where the conditioning is done on the assignments, that you don't always estimate something interesting. And this is true, of course, more generally. The current paper also shows that the two-way fixed effects estimator doesn't always estimate something interesting. So I think this paper does a bunch of things. It furthers our understanding of two-way fixed effects estimation. It shows how important it is to consider the assignment process, except for selected work, like the Callaway and Santana work, for example. There's other work. I've been doing a bit of work with a student of mine where you use inverse probability weights combined with regression adjustment. But as the paper emphasized and Lihua mentioned in the presentation, the kind of double robustness is different. Okay, I'm going to raise this issue again momentarily, because I'm still not quite sure that I'm getting entirely how that works. So I'll raise that question in the simple case. So one of the nice features about this paper is it allows for a general assignment path. So in principle, you can have entry and exit. The transient treatment is a special case of entry and exit. So that is being general in this way, and then modeling the probabilities of these paths is what buys the double robustness result and some resiliency to violations of parallel trends. As the authors are careful to note, that's another thing I'm not surprised, of course, that's admirable about the paper, is that they're quite upfront about the limitations. So where the paper, the approach is not especially general now, is in the output, how about outcome model. So there's linearity there, and I think linearity is often a good approximation. I do think that this idea of trying to figure out how to allow the regression part of it to have more heterogeneity in treatment status would be a very nice addition. So there are other costs, I think, of having a general design mechanism. So if you focus on the staggered adoption where there's no exit, then you can estimate different kinds of treatment effects and many more of them, and then you can figure out later on how you want to aggregate those up. This paper, basically focuses on a single parameter that is of interest. So it's like this equally weighted treatment effect, average treatment effect. Okay, so this, when you look at something like the case study at the end, we may be interested in knowing whether there were different effects depending on when each state declared the state of emergency, for example. In the end, of course, we're going to aggregate that up somehow. So I'm just, reminding you what the general target is. So you'll see, first of all, the treatment effects are averaged across unit. So in particular, none of the units are given different weights. The weighting is all in terms of the time series component. So for example, this is much more of a focus on an average treatment effect, and the notion of an average treatment effect on the treated, at least in the finite population design-based inference setting, doesn't seem to come up. And so one implication of that is, if you use the approach in the current paper and compare it with approaches that in the staggered entry case, and you get different answers, do we really understand why those answers are going to be different? They use overlapping assumptions, and in fact, they're targeting different kinds of parameters in general. And we know that average treatment effects across the whole population and average treatment effects on the treated can be quite different. And so I'm curious to know how one might decide which approach is getting us closer to an interesting parameter in a particular application. And I certainly don't know how I would do that. So just briefly, the paper, which is quite impressive and long, it covers a couple of cases, and Lihua in the presentation covered the case where there is no sampling, so the sample is the population. The paper covers more general cases. This is a small t panel data case, and I think this in lots of applications, this is the most relevant setup, although certainly it doesn't cover everything, but this is the harder case to cover, as Lihua mentioned. Okay, so here's the thing that really is impressive to me and interesting to me, and that is the absence of a parallel trends assumption when the assignments are properly modeled. And so, when you have the assignment mechanism correct. Now, I still am not quite sure how this is realized. Is it because this is for a very specific parameter, and so you can essentially target this parameter so that when you have the assignment probabilities correct, that you can estimate that targeted parameter without the parallel trends assumption? I guess that's related to, is that it, or are there some implicit restrictions on the allowed deviations from parallel trends, or just is it completely unrestricted? I should comment that in the paper, the assumptions, and I should also say that I noticed in the questions popping up that some people clearly had anticipated some of the points and questions that I was going to make, but there is implied by the assignment a so-called no anticipation assumption. So if you're wondering if that's in there, it is. The assignment does not vary with the potential outcomes. So this issue of the sattva assumption already came up. When we make sattva across the cross-sectional dimension, of course, that's an assumption ruling out spillover effects. It does, I guess I was hedging a little bit. Sattva does imply that there aren't going to be any dynamic effects. And so this does make it difficult to compare the current framework, which estimates the static effects, with other frameworks that do allow for dynamic effects. And I'm guessing at some point down the road, these two things will come together, hopefully. And just to remind you, with staggered entry, and I'm using a notation here, which is a sampling notation so that the outcomes are treated as random, we can estimate an average treatment effect for each treated cohort in each relevant time period. And so we get that flexibility by not having such a general framework that looks at the treatment assignment. Okay, so I put too many slides here, but I'll try to jump over things. So one thing that when I've been thinking about some of my work on the staggered entry case, and especially the nonlinear difference in differences with binary and count outcomes, I've been thinking for some time about how to do a doubly robust version of that. I haven't done anything formal with it yet, but this paper, so I'm happy to see this paper because it doesn't do what I would have done, but it certainly gives me some ideas about what I might do in the future. So when t is equal to 2, I guess some things that are, that I haven't resolved in my mind is, we know there are a bunch of equivalent ways to get the diff and diffs estimate with 2 time periods. One would be to do the full 2-way fixed effects regression. The other way is to do a much shorter regression where all we have to do is control for whether a unit is ever treated or not, which means treated in the second time period. So this is the traditional control period in the first period, treated in the second. And these two regressions give you exactly the same coefficient on the treatment variable. And we also know, of course, that first differencing the outcome and doing a pooled regression are the same. I did confirm that the following are also the same, and this isn't too surprising based on the results in the paper. But when I did this, and to tell you the truth, I wasn't really thinking about this, the distinction when I did this, I defined what I thought were the natural probability weights, which vary over time. So these are the probability weights where there's no, the probability of being treated in the first period, which is indicated by that time dummy, is 0. And then some units are treated in the second period, and that estimated probability is given by rho 2 hat. So you can show that both of these weighted regressions, so I would call these inverse probability weighted regressions too, these also produce the standard diff and diffs estimate. Okay, so this makes me wonder, in the paper, that the authors focus on estimating the probability of the entire path. And so these weights actually don't change across time. They change across unit. And so I'm, wondering, is that an important distinction? And, whether it makes sense to think about the weights changing, weighting each time period by a different probability weight. Okay, so I'm running over here, but let me just kind of end it with this then. So in the case of 2 time periods, looking at the Santana Zhao work and, which builds on Alberto Abadi's work, this is what a doubly robust weighted estimator would look like, where you include the treatment indicator, and I knew I was going to make a mistake there. You include the interaction of the treatment indicator with the covariates, and you include the covariates, and then these are the weights that give you a doubly robust estimator of the average treatment effect. So I guess, this has some advantages, of course, because one thing is it allows for heterogeneity in the treatment effect if I had gotten that right, whereas the AILL approach does not. And so, the question is, one, how can that be allowed? But I'll leave kind of with this, and that is, what would in the 2-period case, I guess I would like to see it completely worked out as to where the robustness to violations of parallel trends is coming from when the assignment probability is correctly specified. Because to me, that's really an impressive achievement, because with 2 time periods, you simply can't do anything using this usual kind of approach. The only thing we can do is condition on the x's. So that's the conditional parallel trends assumption. But without having more than 2 time periods, we can't really do anything else in terms of violating parallel trends. Whereas this, the approach in the current paper seems to offer us a way to allow for violations of parallel trends, even though we only have 2 time periods. Okay, so I'd better stop there. The slides are posted. You could see some of my other comments. It really is an interesting paper, and I suspect it'll start being used more once we all understand it even a bit better than maybe we do now. Okay, thanks.
Thank you, Jeff. I think, well, Lihua, do you think you have a 1-minute response to the very complicated and interesting comments, or?
Yeah, maybe I can respond to the parallel trend one, because that seems to be the most important one. And first, I would like to thank Jeff for the very insightful discussion. And actually, I wish you could go through the remaining slides, because that's wonderful. Yeah, so just in terms of parallel trend, I think, yeah, this is a great question. And I had some communication with other people. And it turns out in the finite population setting, it's a very subtle one, that if you assume that you know the propensity score for each person, then this has already assumed that you have unconfounded trend, in the sense that the trend would be the same had you not taken a treatment. But this is different from the usual parallel trend because parallel trend includes both the unconfounded trend and homogeneous trend across units. That's why people often say parallel trend is testable, because you assume that the trend is the same for each person and also same across people. So in that case, you can test parallel trend. But here we only assume the unconfounded trend, while we allow the trend to be different across every unit. So this becomes an untestable parallel trend assumption, if you like. So I think the further distinction between these two types of parallel trend would be very interesting, and it'll be interesting to make it more pronounced. But I'm happy to talk more about that offline.
All right, thank you both. Thank you, Lihua, for the talk, and Jeff for the great discussion and very prepared discussion. Let's wrap up our seminar for today. So next week we have Fan Li from Duke University, who will be giving a tutorial on Bayesian causal inference, and we hope to see you there.